Welcome to the deep dive. I'm absolutely buzzing today because we're plunging headfirst into a topic that, well, sounds like science fiction, but it's very much becoming science fact. Imagine, just for a moment, a computer that doesn't just calculate faster. Imagine one that explores just an astronomical number of possibilities simultaneously. A machine that could solve puzzles in seconds. Puzzles that would take even our best supercomputers years, maybe even billions of years, to crack. That's not just a faster chip, that's quantum computing. It's one of the most exciting and, frankly, revolutionary technologies emerging today. And it promises to reshape, well, pretty much everything. Medicine, finance, national security, you name it.
It really is a staggering prospect. And you're right, this isn't just an incremental improvement, not just a faster version of what we have. It's a fundamental paradigm shift in how we even think about computation. See, your phone, your laptop, all those massive data centers, they run on classical bits, binary, just 0, 1, on or off. Quantum computers, they use quantum bits or qubits. And these qubits have this mind-bending ability to be 0, 1, or crucially, both 0 and 1 at the exact same time, superposition. And that capability just opens up an entirely new realm of computational power, not really for your everyday email or web browsing, but for these really specialized, incredibly hard problems, the kind classical machines just, well, they choke on them.
Exactly. And that's precisely why we're here today, for your personal deep dive into this. Today, you and I, we're embarking on an intellectual adventure straight into the quantum realm. We're not just going to figure out what it is. We want you to really grasp why it's poised to fundamentally alter our world. From, the very atoms used in medicine to the security fabric of our entire digital lives, our mission. Cut through the jargon, demystify these really counterintuitive concepts. We want to deliver a clear, actionable understanding of what quantum computing is, how it actually works, why it's so crucial, what it means for security globally, and importantly, how it's already starting to make a real-world impact right now. We're aiming for those aha moments, Some surprising facts, but without just drowning you in information.
Yeah, absolutely. And to do that, we've pulled together a stack of recent sources, really cutting-edge stuff, all from 2025 or just before. These should give us both accessible explanations and the kind of technical depth you've asked for. Plus, we've got concrete case studies that really show the tangible progress happening, like, right now. It's definitely a complex field, and it's moving incredibly fast. But understanding it, it's vital if you want to stay ahead of the curve on the next technological frontier.
Okay, let's do it. Let's unpack this incredible topic. Our journey starts by decoding the quantum realm itself, getting down to the foundational concepts.
Absolutely. You really need that solid foundation first. To appreciate the power, you have to understand the basic building blocks and the weird rules they play by.
Right. So let's start with what we all know, classical computing. Your phone, your laptop, the internet itself, even like smart home devices. It all runs on classical bits. Think of them like tiny light switches. They're definitely on-and, that's a 1, or definitely OF, that's a 0, end of story. Everything you do digitally, sending a text, running complex software, it's all built from intricate combinations of these simple binary states. And crucially, they're processed sequentially. One step, then the next step, then the next. They're meant to methodical. Kind of like a librarian searching for a book by checking one shelf, then the next shelf, one by one. Efficient in its own way, sure, but totally linear.
Exactly. Now, get ready for a pretty big conceptual leap. Enter the qubit. This is the fundamental unit of information in quantum computing. And this is where things get, well, really interesting and frankly counterintuitive. Unlike that classical bit that has to be a 0 or 1, a qubit can be 0, 1, or, and this is the kicker, both at the same time. This bizarre property is called superposition. It's the first and maybe the most foundational pillar of quantum power.
Ah, okay. Like that spinning coin analogy you sometimes hear. Well, it's flipping in the air. It's not really heads or tails yet. It's kind of both. A blend of possibilities until it actually lands. That's sort of the probabilistic nature of a qubit in superposition. It holds multiple possibilities simultaneously.
That's a great way to visualize it. And this isn't just some quirky difference. It's the source of absolutely immense computational potential. The really profound insight here is how the information capacity grows. It scales exponentially with each qubit you add. Think about this. A system with just 500 qubits can represent more states, more information, than 2 to the power of 500 classical bits. That number, It's astronomical. It's more information than there are atoms in the known universe. Vastly surpasses the capacity of all the world's supercomputers combined. This exponential scaling gives quantum computers this inherent parallelism. It lets them explore and process millions, even billions of possibilities simultaneously for certain kinds of problems. It's like our librarian suddenly gaining the ability to instantly see every single book on every shelf in the entire library all at once, not page by page.
Wow. Okay, that exponential scaling, that definitely hints at something profound. So what are the core principles that really unlock this power? You mentioned superposition, but you said there were others. What else is at play here?
That's right. The real power doesn't come from just one trick. It comes from orchestrating three core quantum phenomena together: superposition, entanglement, and interference. These three working together, that's what drives what people call quantum advantage.
Okay, let's dive deeper into superposition first. It feels really central. You said it allows qubits to be in multiple states at once. How does that actually translate into computational power, like in practice?
Okay, so superposition means a qubit exists in this probabilistic mix of all its possible states simultaneously. So take a quantum computer with just, say, 10 qubits. Small number, right? But because of superposition, it can represent 2 to the power of 10 states. That's 1,024 states. At the same time. Now, picture a classical computer trying to check 1,024 possibilities. It has to do it one after the other, sequentially. The quantum computer, using superposition, can effectively explore all 1,024 possibilities in parallel at once. So the key insight is this massive parallel processing capability. It lets the computer look at a huge number of potential outcomes concurrently. It's not checking one by one. It's exploring everything simultaneously. That's what provides the speed up for certain problems.
Got it. A powerful way to explore a vast solution space all at once. Okay, what's the next pillar then?
Next up is entanglement. This one is, well, it's so bizarre that even Einstein struggled with it. He famously called it spooky action at a distance. When qubits become entangled, they get linked in this incredibly deep way. The state of one qubit instantly influences the state of the others it's entangled with. And this connection holds no matter how far apart they are. Miles, light years, it doesn't matter. It's a connection much deeper than any classical correlation.
Right, because it's easy to confuse this with something classical. Like you have two gloves in separate boxes, one left, one right. You open one box, see the left glove, you instantly know the other's the right glove. But that's different, isn't it? The gloves already were left or right. Quantum entanglement is more fundamental.
It is, and that's a really crucial distinction. Thanks for bringing that up. In the glove analogy, the leftness or rightness was decided from the start. You just didn't know it. With entangled qubits, neither qubit has a definite state, like 0 or 1, until you actually measure one of them. The instant you measure one qubit and it chooses a state, say 0, its entangled partner, no matter how far away, instantly becomes 1, or whatever the correlated state is. Perfectly correlated, instantaneously. The profound insight. Entanglement isn't just some weird quirk. It's the essential glue that allows quantum computers to perform coordinated calculations across many qubits simultaneously. It enables them to work together as a single, powerful computational unit. And critically, you need entanglement for any useful quantum computation. It's not optional.
That is genuinely mind-bending. This instant connection, this coordination across potentially vast distances. Wow. Okay, what's the third pillar? The one that ties it all together.
The third pillar is quantum interference. This flows directly from superposition, and it's how quantum algorithms actually steer the computation towards the right answer. Think about waves in water. They can overlap. Sometimes they add up, making a bigger wave that's constructive interference. Other times they cancel each other out, making the water flatter that's destructive interference. Quantum algorithms are cleverly designed to harness this. They manipulate the qubit states, which behave like waves in some ways, so that the probability waves corresponding to the correct solutions reinforce each other. They get amplified. And simultaneously, the probability waves for the incorrect solutions are made to cancel each other out. Destructive interference diminishes them.
Ah, okay. So the algorithm is kind of nudging the probabilities, making the right answers more likely to pop out at the end and suppressing the wrong ones. That's clever. So the real quantum advantage isn't just one of these things in isolation. It's the skillful orchestration of all three. Superposition to hold all the possibilities, entanglement to link them together for coordinated work, and interference to zero in on the right answer. That is quite a toolkit.
It absolutely is. But, and this is a huge but, there's a major catch. All this incredible quantum power, it's incredibly fragile. These unique quantum properties are extremely sensitive to their surroundings. Which brings us to the biggest practical challenge. Decoherence.
And coherence, yeah, I've heard that term. It sounds like the main villain in the quantum computing story. What exactly is it, and why is it such a massive hurdle?
Decoherence is basically the process where a quantum system loses its quantumness, its superposition and entanglement because of unwanted interactions with its environment. Things like heat, stray electromagnetic fields, even tiny physical vibrations can bump into the qubits. This interaction acts like a premature measurement. When that happens, the delicate quantum information essentially leaks out. Superposition collapses. It snaps back into a classical state, either 0 or 1, before the computation is finished. And when that premature collapse happens, errors creep into the calculation. The results become unreliable, maybe even useless.
So it's like trying to keep that coin spinning perfectly balanced, but the slightest breeze or someone bumping the table makes it fall and land too early, ruining the both heads and tails state.
That's a perfect analogy, yes. This inherent fragility is the #1 physical problem in building stable, reliable quantum computers. To fight decoherence, the physical qubits have to be meticulously isolated from everything. And that often means taking extreme measures, for example, those superconducting qubits used by IBM and Google. They have to be cooled down to temperatures incredibly close to absolute zero. We're talking like negative 273 degrees Celsius or maybe 15 millikelvin. That's literally hundreds of times colder than outer space. Maintaining those conditions requires these incredibly complex, very expensive machines called dilution refrigerators. It's a monumental engineering challenge all on its own.
And then there's the intentional collapse, right? When you actually measure the qubit at the end to get your answer. That's also a collapse, but it's the one you want.
Yes, exactly. That's a crucial distinction. Decoherence is the unwanted, premature collapse due to environmental noise. Measurement, on the other hand, is the intentional collapse performed at the end of the algorithm. You purposefully interact with the qubit to force it out of superposition and reveal a definite classical outcome, a 0 or a 1. It's like finally letting the spinning coin land so you can see if it's heads or tails. In quantum algorithms, these measurements are very carefully timed. They happen right at the end to extract the useful information, the answer the interference guided you towards. It's a fundamental part of the process.
Fascinating. Okay, so we have these amazing quantum principles, but they're incredibly delicate, constantly threatened by decoherence, and only give us a single classical answer when we measure them. Which brings us squarely to the hardware. How on earth do you actually build a machine that can harness this fragile power without it just falling apart computationally?
That is the $1,000,000 or maybe $1 billion question. And it's where the engineering meets the quantum physics in some really remarkable ways.
So when we picture a quantum computer, we shouldn't be thinking of like a quantum CPU chip we slot into a PC, right? What are the actual pieces? What makes up one of these incredibly complex systems, especially needing temperatures colder than deep space?
You're absolutely right. It's not just a chip. It's a whole complex system, way more intricate than a standard CPU. Think of it as an entire ecosystem. At the very heart, of course, are the qubits, the fundamental building blocks. And these aren't just abstract ideas, they're actual physical things. Like IBM uses these tiny superconducting circuits, and as we just talked about, those need to be cooled to near absolute zero to even work to maintain their quantum weirdness.
Right, that extreme cooling. So the qubits are the core, the raw material.
Exactly. Then these physical qubits are housed inside the quantum processor. That's sort of the brain where the actual quantum operations, the gates, happen. Now, to keep things super cold and shield it from absolutely any interference that could cause decoherence, noise, vibrations, stray fields, the whole processor lives inside this massive multi-layered cryostat. That's the super cold refrigerator we mentioned. They can be huge, sometimes looking like these big upside-down nested canister things or like a golden chandelier descending into coldness, each layer colder than the last.
Okay, qubits and processor inside a very, very cold, very shielded box.
Yep.
Got it. How do you actually control them? How do you tell them what to do from the outside world?
That requires incredibly sophisticated control systems. These usually involve things like precisely timed microwave pulses or finely tuned laser beams or controlled magnetic fields. These are like the fingers that reach in and apply the quantum gates to specific qubits at specific times. They orchestrate the whole dance of superposition, entanglement, and interference. And the timing and energy of these pulses have to be unbelievably precise. Mess it up slightly and you cause decoherence. Then, when the computation is done, you need measurement devices, specialized detectors that can read the final state of each qubit, collapsing its superposition into that classical 0 or 1 we can understand. And crucially, perhaps most importantly, given the fragility, you absolutely need error correction systems, because errors will happen due to decoherence. Error correction is key to mitigating this. Typically, this involves encoding the information of one perfect logical qubit across many physical qubits. Using redundancy, things like surface codes, allows the system to detect and correct errors on the fly. Without good error correction, large, useful quantum computations just aren't feasible.
Wow. It sounds like a monumental engineering feat just to get one stable qubit, let alone hundreds or thousands working together reliably. And I understand there isn't just one single way to make a qubit. It's more like a zoo of different approaches, a qubit menagerie.
That's a perfect description, a menagerie. Unlike classical computing, which pretty quickly settled on silicon transistors as the standard, the quantum world is still exploring this wonderfully diverse range of possibilities. You've got superconducting qubits, trapped ions, neutral atoms, photonic qubits using light, even research into exotic things like topological qubits. Different companies, different research groups are backing different horses. This diversity is actually a really clear sign that the technology is still relatively young. We haven't standardized yet. Several different physical systems are fiercely competing to become the foundation for a universal quantum computer. The deep insight from this menagerie is fascinating. The industry isn't just building tech, it's placing fundamental bets on which aspect of quantum physics will ultimately prove the most scalable and fault-tolerant. Each approach is kind of a gamble on physics itself.
So who are the main players in this menagerie? Are there sort of front-runners emerging? And what are the big trade-offs they're making in their choices?
Well, among the various contenders, superconducting systems and trapped ion systems are probably the two leading the pack right now, at least in terms of demonstrated systems and attracting major investment. And they really showcase the fundamental trade-offs companies are grappling with: speed versus stability versus scalability.
Okay, let's tackle superconducting qubits first. That's the IBM and Google approach, right? What's good, what's bad about them?
Correct. Superconducting qubits are tiny electrical circuits made from materials that conduct electricity with zero resistance when cooled way, way down, near absolute zero. Their biggest strength: speed. They allow for very fast gate operations, meaning calculations can happen quickly, often measured in nanoseconds. They also benefit from pretty mature manufacturing techniques borrowed from the regular semiconductor industry. This makes them relatively easier to integrate onto chips, which looks good for scaling up to large numbers. Companies like IBM are really pushing this, processors like their 127-qubit Eagle, and they're aiming for much larger ones.
Fast and manufacturable. Sounds good. What's the downside to these super-chilled circuits?
The main weakness is their extreme sensitivity to noise. Everything disturbs them. This leads to very short coherence times, the time they can maintain their quantum state. We're talking mere microseconds, often. This inherent fragility and the resulting high error rate is exactly why they need that extreme cooling, those complex, super expensive dilution fridges. So the strategic trade-off is pretty clear. They're betting on speed and scaling the number of qubits while accepting higher error rates per qubit. The hope, the assumption, is that powerful quantum error correction will eventually compensate for this fragility.
Okay, so that's one major contender. What about the other one you mentioned, trapped ion qubits? How do they work and how do they compare?
Trapped ion qubits, pursued by companies like IonQ and Quantinuum, take a completely different route. They use individual atoms that have been electrically charged ions as their qubits. These ions are suspended, literally floating, in free space using electromagnetic fields inside an ultra-high vacuum chamber. Then, they're manipulated with incredibly precise laser beams. It sounds like something straight out of science fiction, manipulating single atoms with lasers, but it's real technology.
Wow, holding individual atoms in place with lasers? That sounds incredibly precise, but maybe difficult. What are their main advantages?
Their key strengths are exactly that: high precision and amazing stability. Trapped ion systems boast much longer coherence times compared to superconducting ones, sometimes seconds, maybe even minutes in some lab settings, and they have significantly lower error rates for their operations. This intrinsic stability and precision is really valuable for complex calculations that need long sequences of operations without errors building up too quickly. The fidelity, the accuracy of their gates is often highlighted as a major plus.
Makes sense. And the weaknesses, because there's always a catch with these cutting-edge techs.
Their main challenges are speed and scalability. The operations relying on hitting individual ions with lasers are inherently slower than the microwave pulses used for superconducting qubits. Think microseconds or even milliseconds per gate versus nanoseconds. And as you try to trap and control more and more ions, it gets really hard to aim those lasers precisely at one ion without accidentally nudging its neighbors. That poses significant challenges for scaling up to thousands or millions of qubits. So this approach basically prioritizes stability and accuracy, accepting slower speeds and facing perhaps trickier scaling hurdles down the road.
So it's this fascinating strategic fork in the road. Go for speed, manufacturing ease, or go for stability and precision. It really seems like there's no single best answer yet. It makes the whole race way more interesting.
Not yet, no. And that's what makes this field so dynamic right now. The ultimate winner might not be the absolute fastest or the most perfectly stable qubit in isolation. It might be the technology that figures out how to manage errors most effectively and scales up to a fully fault-tolerant system. And that brings us to probably the most critical development happening in quantum hardware right now: the push towards logical qubits and quantum error correction, QEC. The real breakthrough here isn't just better engineering, it's a deep conceptual shift. We're moving from just fighting fragility to actively engineering resilience using redundancy, building a sort of self-healing quantum computer.
Okay, logical qubits. This sounds like a huge deal, a potential game changer. You're saying physical qubits are inherently noisy and error-prone. How do logical qubits fix that? And what exactly is a logical qubit anyway?
That's the core problem, absolutely. The fragility and errors of physical qubits are the biggest roadblock to practical, large-scale quantum computing. So a logical qubit isn't a single physical thing. It's a more abstract, fault-tolerant construct. The idea is to encode the information of one ideal qubit onto many entangled physical qubits, often arranged in a specific pattern or code. This redundancy, which is the essence of quantum error correction, QEC, lets the system constantly check for errors. If one physical qubit gets flipped by noise or decoherence, the surrounding qubits in the code can detect it and correct it. The information isn't lost because it's spread out, it's protected by this collective encoding. It preserves the delicate quantum state through the computation.
Okay, so it's like having multiple backups, but quantum style, entangled together, so they can collectively fix errors if one physical part fails. That sounds incredibly robust.
Exactly. And this leads to what's arguably the most important metric right now for tracking real progress towards useful quantum computers: the ratio of physical qubits needed to create one logical qubit. Currently, that ratio is pretty high. It can take hundreds, maybe even thousands, of these noisy physical qubits to build just one high-quality, error-corrected logical qubit. But, and this is exciting, recent breakthroughs are showing real, tangible progress. They're proving that this theoretical idea actually works in practice.
That's fantastic news. Tell me about these breakthroughs. What's happening right now that's making this real?
Well, in 2023, Google published a really important experiment. They built two logical qubits, one using 17 physical qubits and a bigger one using 49 physical qubits. And they showed experimentally that the larger logical qubit actually had a lower error rate than the smaller one. This was huge. It was the first real experimental validation that adding more redundancy through QEC actually does improve reliability as you scale up. It proved the theory works in the lab.
Wow, okay. So bigger can be better, more reliable if you engineer the error correction right. That's crucial.
It really is. And others are making strides too. Microsoft, working closely with Quantinuum's ion trap hardware, managed to create 4 logical qubits using just 30 physical qubits, demonstrating some very efficient encoding schemes. IBM researchers also developed new, more efficient error-correcting code that protected 12 logical qubits simultaneously, pushing the boundary on how many logical qubits you can manage and operate at once. That's vital for running actual algorithms.
So quantum error correction, QEC, is clearly the name of the game here. Are there specific types of codes or methods leading the charge?
QEC is absolutely essential. Without it, fault-tolerant quantum computing just doesn't happen. While early theoretical codes like Shor's node or Skeen's code were foundational breakthroughs, the technique getting the most attention now for building large-scale universal quantum computers is the surface code. This approach arranges the physical qubits in a 2D grid, like a checkerboard. It uses clever properties related to the topology, the connections within this grid, to protect the logical qubits encoded within it. It's considered really promising because it's thought to be relatively robust against common types of local errors, and it has a reasonably high error threshold. That means the underlying physical qubits can be somewhat imperfect up to a certain point, and the code can still function reliably.
So this whole shift towards logical qubits feels like a really pivotal moment, moving from just demonstrating weird quantum effects in labs to actually building robust, self-correcting machines that could, reliably run complex calculations over time.
That's a great way to put it. It's exactly that transition from science experiment to potentially viable computational tool. It really is a testament to the incredible ingenuity of the physicists and engineers working in this field.
All right, so we've wrestled with the bizarre quantum rules, the mind-bending hardware, the engineering nightmare of keeping it stable. Now, how do we actually use these things? How do we tell a quantum computer what problem to solve? What's the software side? What's the language of this machine? And what kinds of problems are they actually good at tackling?
Right. This brings us to the world of quantum algorithms. These are the specific sets of instructions, the recipes, designed to run on quantum hardware. And these algorithms are implemented using quantum circuits. You can think of a circuit as a sequence of operations applied to the qubits over time. The fundamental building blocks of these circuits are quantum gates. These are the quantum equivalent of the classical logic gates like A and D or not T gates that run your phone or laptop. But of course, they operate according to quantum rules.
So these gates are what actually manipulate the qubits,
Mm-hmm.
flipping them, putting them in superposition, entangling them.
Precisely. Quantum gates are designed specifically to manipulate qubit states in ways that exploit superposition, entanglement, and interference. They perform operations that are just physically impossible for classical gates. A really key difference is that quantum gates have to be unitary and reversible. Unitary basically means they conserve quantum information and probability no information gets lost during the operation. Reversible means that every quantum gate operation can be undone. You can always run the calculation backward. This reversibility is crucial for preserving the delicate quantum state and enabling those precise interference effects that make quantum algorithms work. It's like having a perfect undo button for every step.
Okay. And just like classical computers have a small set of basic gates that can build up any computation, is there something similar for quantum, a sort of universal set?
Yes, exactly. There's the concept of a universal gate set in quantum computing, too. It means that a small, finite number of specific quantum gates like the Hadamard gate, which creates superposition, and the CNOT gate, controlled knot, which can entangle two qubits, can be combined in different sequences to perform any possible quantum computation. This is super important because it provides the bridge between the software, the algorithm, and the hardware, the physical qubits. The hardware has to be able to reliably perform these specific universal gate operations for any algorithm to run.
Got it. So once we have these gates and circuits, what are the big, famous algorithms, the ones that really show off what quantum computers can do? What are the first movers in this quantum playbook?
There are a few truly groundbreaking algorithms that really demonstrate potential quantum advantage and hint at the transformative power we've been talking about. The first, and probably most famous or infamous, depending on your perspective, is Shor's algorithm.
Ah, Shor's, yes. I always hear that one mentioned with a mix of excitement and, frankly, a bit of fear, especially in cybersecurity circles. Why does it generate such strong reactions?
For extremely good reason. Shor's algorithm is designed to do one specific thing incredibly well: factor large numbers into their prime components. And crucially, it provides an exponential speedup over the best-known classical algorithms for that task. To give you a sense of scale, factoring a large number, the kind used in modern encryption, could take a classical supercomputer billions of years. Shor's algorithm on a big enough, stable enough quantum computer could potentially do it in hours or days. The magic behind it involves something called the quantum Fourier transform, QFT. You can think of the QFT as a kind of quantum superpower for finding hidden patterns, specifically periodicities or cycles, in data. Classical computers are terrible at this. The QFT makes it feasible, and that's key to extracting the prime factors.
And the implications of being able to factor large numbers quickly, why is that such a big deal for, everyday life?
Because the difficulty of factoring large numbers is the mathematical bedrock of most of the public key cryptography we rely on today. Standards like RSA and ECC, elliptic curve cryptography. These are what secure almost everything online. Your secure web browsing, HTTPS, digital signatures that verify identity, online banking, secure email, even the security of many blockchain technologies. If you can run Shor's algorithm on a sufficiently large, fault-tolerant quantum computer, you can break these encryption methods wide open. That has profound, unprecedented implications for data security and privacy across the entire globe.
Okay, that is a massive deal, a direct looming threat to digital security as we know it. What about other important algorithms? Maybe ones that aren't quite so world-breaking, but still show Significant quantum power.
Another really important one is Grover's algorithm. This one offers a speed up for a different kind of task, searching through large unstructured databases or unordered lists. It doesn't give an exponential speed up like Shor's, but it provides a quadratic speed up, which, for really enormous data sets, is still incredibly significant. Instead of checking every item one by one like a classical search, which takes, on average, n2 checks for n items, Grover's uses a clever quantum trick called amplitude amplification. It essentially boosts the probability of finding the correct item, allowing you to find it in roughly the square root of n steps. Imagine searching a massive, completely unsorted phone book for one specific name. Grover's helps you find that needle in the haystack much, much faster than reading every entry.
A quadratic speedup for search. That sounds incredibly useful, since search is fundamental to so many problems in computing. Okay.
Oh, absolutely. And then there's a whole class of algorithms that are especially relevant today in this era of what we call noisy intermediate scale quantum, or NISQ computers. These are the machines we have now getting bigger, but not yet fully fault tolerant, still prone to noise and errors. For these machines, hybrid quantum classical algorithms are really important. Two prominent examples are the variational quantum eigensolver, VQE, and the quantum approximate optimization algorithm, QAOA.
Hybrid, what makes them hybrid? And why are they better suited for today's slightly noisy, imperfect quantum computers?
They're called hybrid because they cleverly split the work between a quantum computer and a regular classical computer. Typically, you give the hard part of the problem, maybe finding the lowest energy state of a complex molecule, or finding the best route for a delivery truck fleet to the quantum processor. The quantum computer uses its advantages, like superposition, to explore the huge space of possible solutions. But because it's noisy, the answer it gets might not be perfect. So the classical computer takes the quantum computer's output, analyzes it, and then provides feedback, adjusting the parameters for the next run on the quantum computer. It's an iterative loop. The quantum part does the heavy lifting of exploration, the classical part refines the search. This back and forth makes the whole process more tolerant to the noise and errors on current machines. That's why VQE and QAOA are the workhorses for many of the near-term applications people are exploring right now.
That makes a lot of sense. Using each type of computer for what it does best. Okay, this is all fascinating algorithmically, but let's ground it. What are the actual real-world industries and applications where people are expecting quantum computing to make a tangible difference? Where will we see the impact?
Great question, and it's worth repeating that key insight. Quantum computing isn't going to replace your everyday laptop for writing emails or watching videos. It's a specialized tool, a very powerful one, but specialized. It shines on problems with exponential complexity, problems involving simulating quantum systems themselves, or really hard optimization tasks where classical computers just run out of steam. And we are starting to see specific applications emerge where this unique power offers a real advantage.
Okay, where should we start? Maybe material science and chemistry. I hear that's a big one. Why is quantum so well suited there?
It's a perfect fit, really, because simulating how molecules or materials behave at the fundamental quantum level, how electrons arrange themselves, how chemical bonds form and break is incredibly difficult for classical computers. The quantum interactions themselves are just too complex to model accurately with the zeros and ones. Quantum computers, though, operate using the same quantum rules, so they are naturally suited to simulating these quantum systems with much higher accuracy. This could revolutionize how we discover and design new materials. Think about developing better catalysts for making fertilizers or fuels, designing more efficient solar cells or battery materials, creating new alloys, or even understanding complex biological molecules for drug discovery. The potential to drastically shorten R&D cycles from years down to maybe months or weeks is enormous.
Are there actual examples of companies trying this already?
Yes, definitely. We mentioned a couple earlier that are great illustrations. Boeing partnered with IBM to use quantum simulations to study metal corrosion, a huge issue in aerospace, obviously. They managed to compute the energy of a key chemical reaction involved in corrosion more accurately than classical methods could easily achieve. But, importantly, their work also highlighted that we still need better algorithms and much better error correction before this becomes truly routine for complex industrial problems. It shows progress, but also the remaining challenges. And then there was that Moderna and IBM collaboration. They used a quantum algorithm, likely VQE, to simulate the structure of a relatively long mRNA molecule, 60 nucleotides. That was the longest simulated to date. Understanding how these molecules fold is critical for designing things like mRNA vaccines. So this points directly towards accelerating drug discovery and vaccine development by modeling biological systems in ways we simply couldn't before.
Incredible. directly impacting things like new medicines and materials. What about finance and optimization? Finance loves complex calculations.
Oh, absolutely. The financial sector was one of the earliest explorers of quantum computing. Why? Because they constantly deal with incredibly complex optimization problems. Things like optimizing investment portfolios to maximize return while minimizing risk, pricing complex derivatives, detecting fraudulent transactions, or optimizing trading strategies. Many of these problems involve juggling a huge number of variables and constraints, and the complexity grows exponentially. Classical computers struggle. Quantum computers, especially using algorithms like QAOA or specialized quantum annealers, hold the potential to find better, faster, more optimal solutions. This could unlock significant value through more efficient markets, better risk management, and personalized financial products.
Any specific examples of financial institutions dipping their toes in?
For sure. JP Morgan Chase has been very public about their quantum research efforts. They've published papers showing theoretical speedups using quantum algorithms for tasks relevant to portfolio optimization and derivative pricing. They've also experimented with using quantum computers for something maybe less obvious, generating certified randomness. Producing truly unpredictable random numbers is surprisingly hard classically, but it's vital for cryptography, risk modeling, and simulations. Quantum phenomena are inherently random, so quantum computers might be a superior source.
Interesting. Okay, last big area, artificial intelligence and machine learning. This feels like a potentially huge synergy. How could quantum help AI?
Yeah, this is a really exciting frontier. Quantum computing could potentially turbocharge certain aspects of AI and machine learning. One area is handling extremely large, high-dimensional data sets. Think about training AI models on incredibly complex data, like medical images or sensor data from complex systems. Quantum algorithms might offer new ways to find patterns or correlations in such data more efficiently. Another area is optimization, which is core to training many machine learning models. Algorithms like QAOA could potentially speed up the process of finding the optimal parameters for an AI model, making training faster and perhaps more energy efficient. There's active research into things like quantum neural networks or using quantum methods for tasks like clustering or classification. It's still early days, but the potential to accelerate AI development or even enable entirely new types of AI is definitely there. It could lead to AI that can solve problems currently beyond our reach.
Okay, so it's clear quantum computing isn't a magic bullet for everything, but for these specific, incredibly hard problems in science, finance, optimization, maybe even AI, it's a potentially revolutionary tool. Which brings us to the really big picture stuff, the strategic implications. Because this isn't just happening in labs anymore. There's a global race, and it has huge consequences for security and power.
Exactly. This technology is rapidly moving beyond pure science and becoming a major strategic factor on the world stage. The quantum computing industry itself is projected to grow explosively. Some estimates put it around $80 billion globally by 2035 or 2040. That's enormous, and what's really telling is how nations are viewing this. Achieving quantum supremacy or quantum dominance is increasingly seen as a national security and economic priority. Much like the space race or the nuclear race in previous eras, there's a palpable global quantum race underway.
A global race. Okay, tell me more about that. Who are the big players investing? And what are the implications if some countries pull way ahead?
The investment levels and strategic goals show a stark contrast. China, for instance, has reportedly committed over $15 billion in national funding since around 2016. That's a massive, focused investment aimed squarely at achieving global leadership, especially in areas like secure quantum communications and networking. The United States, in response, established the National Quantum Initiative, NQI, allocating about $1.2 billion initially to boost domestic research and development and maintain competitiveness. Europe isn't sitting still either. Their quantum flagship program has committed around $1 billion over 10 years, also with a strong focus on quantum communication and building infrastructure.
So it really does sound like a kind of geopolitical arms race, but focused on quantum technology this time.
It has all the hallmarks of one, yes. And this raises serious concerns about unequal access. If the most powerful quantum capabilities end up concentrated in just a few countries, or even a few large tech companies, that could lead to a significant imbalance of power. It could easily exacerbate existing economic divides, create new technological dependencies, and have major implications for national security, economic competitiveness, and even scientific progress globally. It's not just about who discovers something first, but who controls the potentially world-altering applications.
And one of the most immediate and frankly scary implications of this quantum race is the threat it poses to our current cybersecurity. We touched on Shor's algorithm.
Okay.
This isn't some far-off hypothetical problem, is it? It's something we need to worry about now.
It's absolutely a present-day risk, or at least a short to medium-term one that demands immediate attention. As we discussed, Shor's algorithm, run on a sufficiently powerful and fault-tolerant quantum computer, can break the encryption standards, RSA and ECC, that protect so much of our digital world. We're talking secure websites, HTTPS, digital signatures, online banking, secure emails, VPNs, blockchain, the list goes on.
So the arrival of a quantum computer capable of running Shor's, which some experts think could happen within the next decade, maybe 15 years, could basically render much of our current secure communication useless, exposing huge amounts of sensitive data.
Good, Sean. And it gets worse because of the harvest now, decrypt later threat. Malicious actors, maybe nation states, are almost certainly collecting and storing encrypted data today. Data they can't break now. Think government secrets, intellectual property, long-term financial records, healthcare data, classified communications. They're hoarding it, waiting for the day they do have a quantum computer powerful enough to run Shor's algorithm. Then they can decrypt all that captured data retrospectively. The urgency is real. It's why organizations like the U.S. National Security Agency, NSA, have set a deadline 2035 for federal systems to transition to quantum-resistant encryption. That's not a suggestion. It's a mandate driven by national security concerns.
Okay, clear and present danger requires action now. But presumably the cryptography community isn't just sitting idle. There must be work on a quantum shield, right? Ways to protect ourselves.
Yeah, absolutely. The cybersecurity world is working intensely on this. The primary defense is the development and deployment of post-quantum cryptography, or PQC. These are entirely new types of cryptographic algorithms. They're designed from the ground up to be resistant to attacks from both powerful classical computers and future quantum computers. They don't rely on the mathematical problems that Shor's algorithm solves easily, like factoring. Instead, they're based on different, much harder mathematical problems, things like lattice-based cryptography, code-based cryptography, hash-based signatures problems that we currently believe are hard even for quantum computers. The core idea behind PQC is future-proofing, building encryption that can withstand the quantum threat before it fully materializes.
So we're essentially swapping out the mathematical foundations of our encryption for new ones that are believed to be quantum-proof. Is there a coordinated effort to standardize these new methods?
Yes, a major global effort, thankfully. The U.S. National Institute of Standards and Technology, NIST, has been running a multi-year competition and standardization process. They brought together cryptographers from all over the world to propose, analyze, and attack potential PQC algorithms. In 2024, NIST finalized its first set of standards. These include algorithms like Crystal's Kyber, now called MLKIM, for general encryption and key exchange, and Crystal's Dilithium, now MLDSA, for digital signatures. And we're already seeing adoption. Big tech companies like Google are rolling out PQC, often using a hybrid approach initially. They'll combine a traditional algorithm, like ECC, with new PQC algorithm, like Kyber, for the same connection. That way, if one fails, the other still provides security, allowing for a smoother transition. This year, 2025, is seeing broader adoption of these NIST standards, and there are interesting discussions, like from Equantumpi Near, about how quantum might not just break crypto, but also help secure future AI, maybe creating quantum-fortified systems.
So it's not just defense, it's also about building potentially even stronger security for the long term using new math.
Yeah.
Okay. Beyond the crypto arms race, where else are we seeing quantum computing make a real practical difference today? Let's look at some of those case studies you mentioned.
Yeah, we have some really good recent examples showing tangible progress across different sectors. They really illustrate quantum advantage moving from theory to practice.
Okay, let's start with that IBM and drug discovery project from 2024, the one focused on Alzheimer's.
Right, this was a significant collaboration. IBM used their 127-qubit Eagle processor that's a superconducting quantum computer for early-stage Alzheimer's drug discovery. Specifically, they used a hybrid algorithm, the variational quantum eigensolver, VQE, to simulate the complex interactions of a potential drug molecule. The goal was to calculate its energy states very accurately, which is crucial for predicting how effective a drug might be, but extremely hard for classical computers. This involved their superconducting qubits cooled down to 15 millikelvin, using basic quantum gates like Hadamard for superposition and CNOT for entanglement to run the VQE algorithm.
And what did they actually achieve? What was the outcome?
The results were pretty impressive. They reported that the quantum simulation significantly reduced the computation time needed for this specific molecular analysis from potentially months on classical systems down to just days. This faster analysis helped them identify promising drug candidates much earlier in the pipeline by modeling their interactions more accurately than was easily possible before. This could save potentially millions in downstream experimental lab testing costs. Importantly, they also highlighted the use of advanced error mitigation techniques, ways to reduce the impact of noise even without full error correction. These techniques improve the accuracy of their results by about 30%, which is critical for getting trustworthy answers in sensitive areas like drug design. It really shows the potential to transform R&D pipelines.
That's a clear, measurable impact on healthcare R&D. Faster results, potentially saving money and accelerating the search for cures. Okay, what about that Google quantum supremacy claim back in 2019? That made huge headlines. What was that all about?
Yes, the supremacy experiment. That was definitely a landmark moment, generating a lot of excitement and debate. Google used their 53-qubit Sycamore processor to perform a very specific, highly contrived task, sampling the output of random quantum circuits. They showed their processor could do this task in about 200 seconds. They then estimated that the most powerful classical supercomputer at the time, IBM's Summit, would need roughly 10,000 years to perform the exact same task. The Sycamore chip used superconducting qubits and ran complex sequences of quantum gates to generate these really complex random number distributions. They verified the results using a statistical method called cross-entropy benchmarking to show the quantum computer was genuinely producing results consistent with quantum mechanics and hard to simulate classically.
Right, but there was some pushback, wasn't there? IBM argued that with better classical algorithms, their supercomputer could actually do it much faster, maybe in days, not 10,000 years.
Exactly. There was a very healthy and important debate. IBM pointed out that Google's classical comparison might not have used the absolute optimal classical approach and suggested their Summit machine could potentially solve it in a few days with enough memory and clever algorithms. Regardless of the exact classical time, the experiment was still hugely significant. It undeniably demonstrated a quantum processor performing some task far beyond the practical reach of even the best classical supercomputers at that time. It was a proof of potential. Since then, by 2025, Google, like IBM, has largely shifted focus towards building error-corrected systems capable of running more practical algorithms. They acknowledged that decoherence was a major limit in the Sycamore experiment. Coherence times were microseconds, necessitating very fast gates just to complete the calculation before the quantum state fell apart. The supremacy benchmark proved a point. Now the push is for useful, fault-tolerant machines.
Still, a milestone in showing raw quantum potential. Okay, let's shift gears. Tell me about EPB and quantum networking in Chattanooga, Tennessee. That sounds like a much more immediate, practical cybersecurity application happening right now in 2025.
This is a fantastic example of quantum technology being deployed for real-world benefit today. EPB is a city-owned utility company in Chattanooga. They partnered with a quantum tech company called Quibitech to launch a quantum network. Specifically, they're using it to test quantum key distribution, or QKD, to enhance the cybersecurity of their critical infrastructure communications. Their system uses photonic qubits, single particles of light sent over standard fiber optic cables. They use a well-established QKD protocol called BB84. This protocol uses the quantum properties of photons, like their polarization, to allow two parties to securely generate a shared secret encryption key.
And the big selling point of QKD is that it's inherently resistant to eavesdropping. If someone tries to listen in, immediately.
Precisely. That's the killer feature. According to the laws of quantum mechanics, if an eavesdropper tries to intercept and measure the photons carrying the key information, the very act of measuring disturbs the quantum state of those photons. This disturbance creates detectable errors in the communication channel. The legitimate sender and receiver can monitor for these errors. If they see too many errors, they know someone is listening in. They can then discard that compromised key and start generating a new one over the secure channel. So EPB is using this to physically secure their municipal data transmissions, reducing the risk of cyber attacks on vital city services. It's also laying important groundwork for potentially building out larger quantum-secured communication networks, maybe even a future quantum internet. It's a tangible quantum security solution deployed in the real world.
Very cool. Tangible security benefits right now. Okay, one more. Volkswagen optimizing traffic back in 2019. How did quantum computing help with traffic jams?
Yeah, this was a fascinating early application using a different type of quantum hardware, a D-wave quantum annealer. These machines are specifically designed for optimization problems, not universal quantum computing. VW used it to tackle traffic flow optimization in Beijing, a city famous for its gridlock. They formulated the traffic problem as a QUBO, quadratic unconstrained binary optimization problem. QUBO is a mathematical way to frame many optimization tasks, basically asking the computer to find the best on-off O1 settings for a set of variables to minimize some cost function, in this case traffic delay. They used about 400 qubits on the D-Wave machine within a hybrid quantum classical workflow to find better timings for traffic lights and potentially suggest optimal routes for a set of vehicles.
And did it actually work? Did it reduce traffic tests?
According to their reports, yes. They claimed the optimized routes and timings led to a reduction in traffic delays by around 15%. In a massive city like Beijing, even a 15% reduction translates into significant savings, less wasted fuel, lower emissions, less time stuck in traffic for commuters, millions in potential economic benefits. VW indicated they plan to scale this approach to other cities, showing how quantum optimization, even specialized forms like annealing, can offer real-world benefits for complex logistical problems like urban traffic management. It brings quantum down to improving everyday life.
These examples really drive home the point. Quantum isn't just theory anymore. It's starting to deliver tangible results, from discovering drugs and securing networks to optimizing traffic flow. And looking even further ahead, there's this grand vision of a quantum internet. What does that future look like?
That's the really ambitious long-term goal. An unhackable global network that uses quantum entanglement itself for fundamentally secure communication. Imagine sending information encoded in entangled particles, where any attempt to intercept it instantly breaks the entanglement, alerting the sender and receiver. It could revolutionize secure communication for governments, finance, everyone. We've seen some impressive early milestones pointing in this direction. China's Michia satellite demonstrated intercontinental quantum key distribution back in 2017, and they've built large-scale terrestrial QKD networks spanning thousands of kilometers within China. These show long-distance quantum communication is feasible, at least for key distribution.
But I guess there are still major hurdles before we have a true global quantum internet, where complex quantum information, not just keys, can be sent reliably over vast distances.
Oh, absolutely. Huge hurdles remain. Current QKD is generally point-to-point and has distance limitations without trusted relays, which kind of breaks the end-to-end quantum security promise. And crucially, QKD is mostly about distributing classical keys securely using quantum means. It doesn't usually involve sending complex quantum states, qubits themselves, over the network for things like distributed quantum computing. Building a true quantum internet that can reliably transmit entanglement and qubits over global distances will require breakthroughs in technologies like quantum repeaters to extend the range without destroying the quantum state, and quantum memory to store quantum states. Most experts think a full-fledged quantum internet is still decades away. It needs sustained, significant R&D investment to overcome these fundamental engineering challenges.
So a visionary goal, but one requiring patience and continued innovation. Okay, let's bring it back to the present and near future. What about the human factor? All this amazing technology, how is it going to impact jobs, society, and what are the ethical considerations we need to be thinking about?
The societal impact could be profound. On the one hand, the rise of a quantum economy will definitely create new, highly specialized jobs. We'll need quantum algorithm designers, quantum hardware engineers, technicians to run those complex cryostats, quantum software developers, quantum network specialists, entirely new career paths. But on the other hand, it also means existing workforces will need retraining and upskilling. Quantum-enhanced AI or optimization software could automate highly complex tasks currently done by humans, think logistics planning, financial modeling, materials discovery. The workforce will need to adapt to integrate these powerful new tools, shifting from performing the calculations to managing and interpreting the results from these quantum-powered systems.
And beyond jobs, I imagine there are deeper ethical questions, especially given the power to break encryption or supercharge AI.
Definitely. A major concern is the potential for increased economic inequality. If access to practical quantum computing becomes heavily concentrated, maybe only affordable by large nations or giant corporations, it could create a significant quantum divide. Those with quantum capabilities could gain enormous advantages in areas like finance, drug discovery, materials science, code breaking, and AI development, potentially leaving others far behind. This could deepen existing societal divides and concentrate power in dangerous ways. It really is a dual-edged sword. We have to balance these serious risks and proactively think about equitable access and responsible governance. At the same time, we have to recognize the incredible potential for good using quantum computing to tackle huge global challenges like climate change through better modeling, discovering new energy sources, better catalysts or materials, developing personalized medicine, and creating materials that could improve lives worldwide. It's a very fine line to walk.
Immense potential matched with immense responsibility. Requires careful thought, global collaboration, and ethical foresight as this technology matures. Hashtag tag outro. And that, incredibly, brings us to the end of this deep dive into quantum computing. What a journey. We've gone from the truly weird, almost unbelievable rules of quantum mechanics, superposition, entanglement, interference, all the way to seeing how these principles are being harnessed in actual machines. Machines that are already starting to make a tangible impact, and why this technology is becoming such a critical strategic issue for everyone.
Yeah, the key takeaway for you, I think, is just how transformative quantum computing promises to be and the sheer speed at which it's moving now. It's really shifting from a lab curiosity to a practical, albeit specialized, computational tool. And those recent breakthroughs in logical qubits and error correction, they are absolutely crucial. They signal a clearer path towards building fault-tolerant machines that can solve real problems. And we've definitely seen its dual nature. It's a serious cryptographic threat we must address now with PQC, but it's also this enormous, unprecedented opportunity across nearly every field of science and industry. It promises solutions to problems we previously thought were simply impossible to solve.
Now, for those of you listening who are thinking, okay, I want to try this, you don't need a basement cryostat. You can actually access real quantum computers right now through the cloud. Platforms like IBM Quantum, Amazon Bracket, Microsoft Azure Quantum, they offer online programming environments and access to their actual hardware. If you want to learn more, I'd suggest checking out Qiskit Tutorials. That's IBM's open source toolkit. It's pretty accessible. Or look into online courses like those from MIT for a deeper dive and some hands-on coding. And if you're in business, the advice is clear. Start planning your migration to post-quantum cryptography now. Don't wait. And begin exploring if quantum algorithms for optimization or simulation could give your organization an edge. Because this future is arriving faster than many people realize.
It really is evolving at breakneck speed. Nations, corporations, they're pouring billions into this race. So maybe the provocative thought to leave you with is this. Given these rapid advances, this intense global competition for quantum supremacy, how do you think this delicate balance will play out over the next decade? The balance between the incredible opportunities, new medicines, clean energy, scientific discovery, and those profound security threats. How will it reshape geopolitics, national power, and the very fabric of our digital existence? And what responsibility do we all have as a global society to try and steer this immense power towards collective benefit?
Definitely a lot to chew on there. A huge thank you for joining us on the deep dive today. We hope you found this exploration into the quantum realm both enlightening and thought-provoking. We'll catch you next time.